I'm going to discuss another example under substitution method. Let's see how this example can be solved using substitution method. The given recurrence relation is T of n equals to T of n minus 1 plus n. The condition here is when n is greater than 0. When n is equals to 0, it is a base case, we get some constant time here. Let's take the recurrence relation T of n equals to T of n minus 1 plus n. This is equation 1. So, if you want to derive the complexity, you need to know what this T of n time taken to solve this n minus 1 size problem is. So, T of n minus T of n, we already know it, we have the question. So, we know what exactly the T of n is. So, if you want to know T of n minus 1, so if you want to know T of n minus 1, substitute n minus 1 in the place of n here in this equation. So, T of n minus 1 equals to T of, here if you substitute n minus 1 in the place of n minus 1 minus 1, which is going to be n minus 2, plus again there is n here, in the place of n we are supposed to substitute n minus 1. So, this is what T of n minus 1 is, T of n minus 1 equation is. So, now you know what is T of n minus 1 is. Substitute equation 2 in 1 now. In the place of T of n minus 1, we are supposed to substitute this equation now. So, now your T of n is going to be T of n minus 2 plus n minus 1 plus retain this n. Again, if you check the equation, you need to know what exactly this T of n minus 2 is now. So, T of n minus 2 is, again you know what is T of n is. So, substitute T of n minus 2 in this n. So, you would get T of n minus 2 minus 1, which is n minus 3, because here n minus 2 it would be. So, n minus 2 minus 1 is going to be n minus 3, plus again n is there, wherever the n comes you are supposed to write n minus 2. So, you know what is T of n minus 2 is, right. So, now in the place of T of n minus 2, you can substitute this equation 4. Substitute equation 4 in 3. T of n equals to, now you know what is T of n minus 2 is, it is T of n minus 3 plus n minus 2, and already in T of n there is n minus 1 plus n is there. So, write n minus 1 plus n. This is going to be our equation 5. Then again, if you want to derive it again to reach the time complexity, you need to know what is T of n minus 3 is. Again, in the place of n, if you substitute n minus 3 in this equation, you would get T of n minus 3 minus 1, which is T of n minus 4 plus n minus 3. This is equation number 6. Now, you have T of n minus 3 is, it's here. Substitute now. You would get, so you have to, we need to get the sequence by keep substituting the formulas. So, already somehow we got the sequence now. Okay, again we will write it like we substitute n minus 3 now on T of n now. So, now T in the place of T of n minus 3, write this entire equation T of n minus 4 plus n minus 3 plus n minus 2, already these 3 were there, right. You are supposed to retain it in n minus T of n plus n. So, somehow we got the sequence now, right. So, it would keep on going like this. Again, you need to know what is T of n minus 4 is. So, recursively it would keep on going like this. So, we got a sequence now. We kept substituting the formulas and we got a sequence now. So, when it would end till some extent, till we reach the base case, till some values it would be going, right. So, here if it is 4, here it is going to be 3, here it is 2, here it is 1, it keeps going like this, right. So, if this is k, if this is k value, this is going to be k minus 1, this is going to be k minus 2, and this is going to be k minus 3. So, it keeps going like this. This is what the sequence is, right. So, till some n minus k value it would keep on going. So, if you write it, if you write it in a sequence, this can be written like this: n minus 3 is going to be k minus 1. If this is k, this is going to be k minus 1. Then again n minus, this 2 is going to be k minus 2. Then again n minus k minus 3 till some n, it's going on, right. T of n equals to. So, when it would end, when this becomes 0, it would end, right. So, you make this term 0. t of n minus k, right? So it can be written like this, n minus k equals to 0, which means n equals to k. In the place of k, if you substitute n, this would become 0, right? So t of n minus n, which means this became 0, right? Plus, again on all the case, if you substitute n minus in the place of k, you substitute n, you just multiply it inside, minus into minus, plus 1 plus again n minus, in the place of k substitute n, then again plus 2 plus n minus n plus 3. We would keep on going like this till some n, right? Now if you cancel it, these two would get cancelled, so this would become 0, and again n and n would become cancelled, then it is 1 then again n would get cancelled, so it would be only 2 would be remaining, again n and n is cancelled, 3 would be remaining, till some n it would be going. I think now you would have got the sequence. This is sum of n natural numbers, right? Formula of sum of n natural numbers. This t of 0 would become 1. So 1 plus, this indicates the sequence, right? Sum of n natural numbers, n into n plus 1 by 2. So if you ignore all the constant, so finally the most dominant term would be considered as a final complexity. So when you multiply it inside and ignore all other constants, you would get the complexity as n square. So it can be represented as big O of n square. So for the given recurrence relation here, t of n equals to t of n minus 1 plus n, the complexity is going to be n square. So until you get the sequence, you find the sequence, you are supposed to keep on substituting it, and finally like till some extent it would go. So find the sequence and end it, and find the formula, which formula sequence is followed here. You have to identify it and derive the final complexity through which. So this is how the substitution method can be applied to solve the recurrence relation. Thank you.